Hello and welcome to another LeetCode video. Today we're going to be doing problem number 148, sort list. And it's an interesting problem because we are going to be doing a sort, but now we don't have an array, we actually have a linked list, so we'd have to figure out how that would work. And there are common problems that you either have to do this on parts of a list, or basically you're using this as a subproblem to do something else. So doing this or doing reverses on linked list is going to be something that you're going to want to know for sure. Okay, so let's take a look at this problem. So given the head of a linked list, return the list after sorting it in ascending order. So we have list 4, 2, 1, 3. And now we want to sort it. Well, there are different algorithms to sort, but what I'm going to be introducing is a merge sort. You can do I think it's probably the easiest one to do, and I think it makes the most sense with list nodes, because you could do other sorts. You could do a bubble sort or something, but realistically, honestly, the only sorting algorithm, well, at least one of the few that I know how to do off the top of my head, is a merge sort, and maybe a heap sort. But the nice thing is it's also one of the most efficient sorting algorithms, so it is an n-log-n sorting algorithms. I think there's also quick sort and heap sort, but we don't want to use extra space here. So we're just going to use the, I think we could technically use a heap sort, and that wouldn't be extra space if we just delete all of these connections and we put our nodes in a heap. Technically, that would be considering extra space, but we're going to do a merge sort here because I do think it's a little bit trickier to execute than a heap sort, and also it's with a linked list, so it's going to add some complexity here. But anyway, we're going to want to sort this, and the way that merge sort works is, let me actually show you. Basically, what we need to do is it's like a divide and conquer problem. We need to be dividing our list up until we have one node. So let me show you what that's going to look like, right? So in the beginning, if we have an even list, we're going to divide it up like this. Get rid of this. Then we have these two subproblems. Now for the left subproblem, we have two nodes, so we have to divide that up again. Delete this. Divide this one up. And now we are going to actually be merging recursively. So we're going to merge these two, then we're going to merge these two, and then we're going to merge that whole thing. So let's take a look what that looks like, right? So for a 4 and a 2, we're going to merge a 4 and a 2. Well, it's pretty straightforward for just two nodes, right? It's just going to be 2, 4 here. So we're going to have 2, 4. So that's going to go over here. 2, 4. And then for this 1, 3, it's going to be the same thing. It's only two nodes, so we're going to merge them. So that's going to be 1, 3. And now we are going to merge these two lists together, right? So we have a 1, 3. I'm not going to draw the arrow, but imagine there is an arrow. 2, 4. Actually, I could. Doesn't matter. Okay, so let's draw this. So we have to merge these two lists. And now this problem is also like a LeetCode Easy or LeetCode Medium, right? Where it's merged two lists that are sorted. And so once we know that, then it's pretty straightforward. We just go through the lists and we need to just check what element is smaller, and that's all we have to do there. And so we're going to go through these lists, and like I said, this is once you get to this point where we have two sorted lists, it's pretty straightforward. We just have some index where we're at, we just compare the values, and then we take the smaller one. So we would take the way it would work. Let me just give me some more space here. So the way it would work is if we have this 2, 4, so we're going to have a pointer to each of these, and then we're going to say we're going to have a dummy node that's going to start. And then we're going to say, okay, let's take the smaller value. So the 1 would be the smaller value here. We're going to move this over here. Now the pointer's here. Now we have a 2 and a 3. So the 2 is smaller. And then we're going to move that over here. Now we take the 3. And then now this is pointing to none. So whenever we have a none, we just always take the other one. So this is 4. And then we stop when they're both pointing to none. And then we just return the next pointer of the dummy node. So that's how you do the merge. So remember we have two steps. We have a split step where we keep splitting our list into sub-elements. And then we have a merge step. And so let's actually talk about the split step real quick. And I'm going to show two different examples. So let's say we have these nodes. There's a couple ways you could do it. You could do it like the brute force kind of, or you could do a clever trick. So the brute force is you start here, you just go down the list, and we can just get like a count, right? So we start here, we go down the list, we figure out how many nodes are in here, and then you figure out like okay, well, let's say the count is 4. That means I have to start here. That means I have to move up whatever nodes, like 1 or 2. So you would just do that in a loop. You'd move up like 1 or 2 nodes, and then you'd have this pointer here. Then you just say like, okay, let's take the next node of this node, and that's going to be my second like linked list that we're going to be splitting. And so we're going to have that be this node. So this will be like, the first list. This will be the second list. And then we just take this connection and delete that. But there is a tricky way to do that. And so I'm going to show that. And the way to do that, and I think this works for any list. So for a list with 4 nodes, we're going to want to split down the middle, right? We're going to want to have 2 and 2. And so the way we're going to do this, we're actually going to have a slow pointer here and a fast pointer here. And what we're going to do is our condition is actually going to be this. Let me get a little smaller. 30. So it's going to be while fast and fast.next. And let me show you why. So that's going to be our condition to execute the loop. So clearly here that condition is true, right? So the fast node has to exist and the next node of that has to exist. So let's actually work that out. So this is true for the first case. Now what we're going to be doing is we're going to move the slow pointer up 1 node. We're going to move the fast pointer up 2 nodes. So let's take a look what that's going to look like. So iteration 1, this is true. So our slow is going to go over here. Actually, let's just draw it here. This is gone. And now the fast pointer is going to go up 2 nodes, which will be over here. And now when we go into this loop again, so fast.next does not exist. So we're going to end here. And so you can see that the slow pointer is going to be the node right before the node we care about. So then we could just say like, like second node or whatever it is, or second list equals s dot or slow dot next, And so that would give us this node. And then now that we have this node, this will be the second linked list, and then all we have to do is break this connection. And then we can now we just do the sub problem for the rest of it. So that's how you would split a list with 4 elements. So the 2 cases are odd or even elements, right? And by the way, we can also test this with 1 element. So our base case is 1 element. So with 1 element, we wouldn't even do this. With 2 elements, it would work as well because the fast would be here, the slow would be here, and then we wouldn't even go into the while loop. And so we would split right here. So that would work. Let's look at 3 elements. So with 3 elements, what would happen is the while loop would be true, so the slow would go over here. The fast would move 2 up, so it would actually come over here. And now our fast is out of bounds, so it wouldn't happen. And so we'd break here, which is fine, right? So for a linked list with an odd number of elements, you can either split it with like the more number on the left or the more number on the right, right? So if this is like 5, we can either split it into this or this. It doesn't really matter, right? Well, like when we merge them, it doesn't really matter. You can modify this a little to split in whatever way you want. And for other problems, like some problems are going to want you to split in this way. Some problems are going to want you to split in this way. So you could just slightly modify this fast algorithm. I think it's like you just modify where the fast pointer starts by a little bit, and then that will change your outcome for that. But in this case, it doesn't matter. But anyway, let's walk through a 5 element list as well. So let's say we have 1, 2, 3, 4. And yeah, now we don't really need to keep track of like a current or a count. We just have these slow and fast pointers. So we would have a slow and a fast. And let's see what that would look like. So we can move them right away. So let's move it here. Now the fast is going to go over here. Now there is a fast and a fast.next. This is still true, so we can move again. So the slow is going to come over here. Fast is going to be out of bounds. And so we are going to chop right here, which is fine, right? We're going to have this list and this list. So totally fine. And so that's going to be how our split's going to work. And then what we're going to do is we're going to merge the nodes that we split. So we need to write a splitter function that splits, and then we need to merge. And so what that's going to look like, let me draw that. So like for a list like this, we're going to say merge, and then we are going to actually split this thing, right? So we are going to split the left and then split the right. So it's going to be split, the left part and then split the right part. And so what that would look like is the left part is going to be, so let's just say this is M, it's going to be S. And so this is going to be 1, 2 here. And then split the right part is going to be 3, 4. Like we call this after we already made our initial split. And so if you think about it recursively, then okay, you'd have this 1, 2. So what would that look like? Well, so once we have this recursive case, then it's pretty straightforward because this is going to break down into this. And so remember, the split of 1 would return 1, and the split of 2 would return 2. So we would have a merge of node 1 and node 2, which would give us this. So that would give us this over here would give us 1, 2 sorted. So now we have like the value that actually gets returned into this would be 1, 2. And now for 3, 4, it would be the same thing, right? So when we try to do this subproblem, this split 3, 4, what's going to happen is we're going to chop it up like this. And then when we call split on 3, split on 4, and we merge those, then that's going to return to us 3, 4. And so 3, 4 is going to be returned into here, right? So now once we actually recurse back, our stuff is going to look like merge these two lists, which is what we want. So that's kind of how it works. We chop up the list, and then we call, and this is going to be the function that we need to call. So we do need to write a merge function, and then we need to call a split function, and then we just need to call split on, because split is going to call merge in it. So we need to call split on the head of the list, and that will give us the new linked list. And so let's do that. So first we are going to write the merge function. So let's do that. And this is, like I said, this is just another LeetCode problem where you're given 2 sorted lists. So we can just call that list 1, list 2. Okay. And we can definitely handle, I don't think we can ever have a list of no elements. I'm pretty sure we can debug that later. I think these lists have to be non-empty, because when we split and we have a list of 1 element, it would just return. It wouldn't try to split it again. Okay, so we can assume that list 1 is non-empty and list 2 is non-empty here. So we do the same thing we always do. So we make a dummy node. So the list node here. We don't have to give it a value, so we just do this. Then we say while list 1 or list 2. So I think in some of my old problems I had like 3 while loops. I'm going to show you how you can write this in 1 while loop just to make it cleaner a little bit. So we can say, so this is always going to be true if one of the nodes exists. So you could say if not list 2. So if there's not list 2, we're always going to be taking from list 1. Or, and then this is going to be left. This would be list 1, right? So if list 1.val is less than list 2.val. Okay, then we're going to want to use list 2.val. So, we also need to make a current node. So cur dummy, as usual. Okay, so now this is going to be cur.next. So this means we're going to be taking from list 1, guaranteed, right? If there's not list 2, then we have to be taking from list 1. And if list 1.val is less than list 2.val, we're also taking from list 1. So that's going to be a list 1. Yeah, and we just want to take that node. Yeah, perfect. Now what we want to do is we want to update list 1. So list 1 equals list 1.next. Okay, so now we need to actually move up this node. So this is going to be, actually no, what we need to do is we need to break the connection between, yeah. So like, for example, like let's say we do have this dummy node and we're processing a list. Let's just say 1, 2, 3, whatever, like 1, 2, 3. And then our current node is somewhere over here. Let's just say it. So actually the current node is this node. So what we did was we said this is this, and this, like this, let's just say this is L1. We actually moved it over here. So that L1 does not exist. But now what we need to do is we need to break this connection right here. Let's do that next. And that's going to be cur equals cur.next. And then we can just break it here. Yeah, cur.next equals none. Okay, so we broke it there. Now else we need to be taking from list 2. So that's just all the same stuff. List 2 dot, list 2 equals list 2 dot next, cur equals cur.next, cur.next equals none. Okay, so that should deal with that. Now we just need to return the dummy.next, which is the head node of our new list. Okay, so this is the subproblem for that. And if you want to look into that, I think in my easy speedrun, I do have like, I actually did this exact problem, pretty sure, and in some other ones. Okay, so now we need the other function, and that's going to be the split function, right? And so the split function is going to do the same thing. It's going to take list, no, it's actually going to take one list. So the split function is going to take one list and split it into two. Yeah. Like when we have this 1, 2, 3, 4, it's going to take this one list and split it into two, and then it's going to merge. Yeah. So it's going to split and merge, but we need to call this merge. Okay. So for our base case, if the length of list 1 is 1, then we're already like done sorting it and splitting it. That's pretty straightforward. So list1.next does not exist, so not. And we can return straight away. Okay, now we need to do this slow and fast thing. So slow fast equals list1, list1.next. And then, like I said, do I still have it saved? No, I don't, but it's going to be well fast and fast.next. Slow equals slow.next. Fast, remember we move the fast up twice. Okay, so now the slow in our picture, the slow pointer is going to point to this node. And so now what we need to do is we need to save the node after it, and then we need to make a break here. So let's do that. So let's just call this list2 equals slow.next, and then slow.next equals none. And now we need to return, remember we are merging the split of like the next part. So that's going to look like this. It's going to be merge, and it's going to be split. We need to do a subsplit again, like this is the recursive case. So we need to split list. It's not going to be list 1. This is going to be, no, it is going to be list 1. Yeah. List 1, list 2. Because now our list 1, so for example, like let's actually show what that looks like. Like we did have a list 1, like this. So let's say this is list 1, okay? And so what we did was I mean, this 3 is a little bad, but let's actually fix it so it's more legible. Okay, perfect. Okay, so what we actually did was our slow was going to end up here, and so we chop here, and this is going to be list 2, this is going to be list 1. But because we chopped here, now these two lists are actually split. So list 1 is 1, 2, and then list 2 is 3, 4. So now we need to call split on each one of these lists because we need to do like a recursive subsplit, and then we need to merge all that together. So we're going to call split on 1, 2, which is going to keep splitting, and then it's going to merge that into some sublist, and then we need to do the same thing here, merge that into some sublist, and then we need to, so split, and then when we split, it's going to have another merge and so on. Okay, so I think that should be right. Now, finally, we just need to just check for these variables. Can you have like an empty list or something? Yeah, so it looks like there is a case where we are given an empty head, but we never actually handled that. But that's totally fine. We can just check for it here. So we can say, if not head, return none. That should take care of that issue. Now our list is guaranteed to be at least one item, and then the split will just return that one item. Okay, so now we need to do one last thing. We need to call split on the head. And I think that should be it. So hopefully we didn't screw it up. Oh, right. So this needs to be split list 1, and then we need to split list 2. We need to keep trying to split them until we get to the recursive case. So I don't know how many parentheses I have here. Maybe too many. Let's see. If not list 2, or let's think about this. So if not list 2, then it will do list 1. Yeah, that seems fine. Or if not list 2, that means list 1 has to exist. But what if there's no list 1, right? Or Yeah, so we might have to just check for list 1 here. Because, like, what if there's a list 2 and not list 1? That would be the case. Yeah. Okay, so list 1 and that should be fine. Hopefully. Okay. Nice. Okay, so let's think about the time and space here. But yeah, you can technically break this while loop down into multiple, but we did it the cleaner way this time. I think there's actually a way to even do it cleaner than this, but at least this makes it all better. Okay, so now let's think about the time and space here. So what are we actually doing? Well, I guess we know for the time and space, right? This should be n log n because this is a merge sort. So n log n is guaranteed to be, merge sort is guaranteed to be n log n because we're going to split the list n times, and then for each like sublist, we need to merge that. And so that's going to be n log n. Okay. For the space, so it's going to be O of 1 because we didn't actually make like any new lists. We're just splitting the nodes. We're using the nodes we have. We're not creating any new nodes. We are creating this dummy node, but we're deleting it every time. We're not actually like adding it to the list or anything. So that should be constant extra space. So that's the key with these linked lists. To make these functions efficient, you need to make sure you kind of sort the lists. You sort the nodes in place, and it's a lot easier for linked lists because we just break up the pointers and move the nodes around, right? So it's a lot more straightforward than like with an array to sort it in place and things like that. Okay, and yeah, I think that's all for this problem. So hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching. Bye.